Okay, so in the last lecture we solved the problem using the vector analysis and the displacement we defined earlier. In this lecture we're gonna start discussions on the motion of an object. Okay, we're gonna start with motion in one dimension, then we are gonna move on to 2 dimensions. Okay. So motion in one dimension, if something is moving in one direction, you can always call that direction x direction, right? And then the displacement, velocity, acceleration, they can only have one component, right? X component, okay? So the simplest motion in x direction is gonna be when something's moving with a constant velocity, okay? So if something's moving with a constant velocity, then the acceleration is 0, right? Because the acceleration is the change of the velocity divided by change in time. So velocity is not changing, acceleration is 0. We call this motion uniform motion, okay? And then in this case, the theory for uniform motion, that's very straightforward. That's very intuitive. Say if you want to find the velocity at any time, actually, you don't need to find it, right? It's gonna be a constant, okay, all the time. So if you want to write this theory, you can write it this way, right? You pick a point initial, you pick a point final. You call them initial and final points. The velocity is always gonna be the same, right? And then if you want to predict the distance it travels in a certain amount of time, you just rearrange the definition of the velocity, right? So the distance travels, it's always going to be the velocity in x direction, and then because the velocity is the same, okay, so we can always use the velocity, the initial velocity at the very beginning of the motion, multiply that by the time, okay? So that's very intuitive, that's straightforward. That's only true for uniform motion, the simple motion, one-dimensional motion, right? And if you make a position and time plot, okay, so you're gonna get the plot on this slide, right? Slide 5. You're gonna get a straight line, okay? The distance is gonna increase with the time linearly, so you're gonna see a linear relation, okay? Because the distance is always gonna be velocity times time, and this is a constant, right? So this is velocity, the slope of this straight line, so it's a constant, all right? A real life example is when you drive a car under cruise control, okay? All right, so that's not much we need to say about one uniform motion, because that's the simplest one, right? It's very straightforward, very intuitive. So the second simplest motion is when, but as I said earlier, it's actually very hard to find things moving at a constant velocity in real life, right? Things are changing all the time, okay? Even if you drive a car using cruise control, you can do that like for, you know, very long time, usually a very short amount of time, right? So when the velocity changes, there is an acceleration, right? And then the simplest accelerated motion is when the acceleration is constant, okay? So that's the simplest accelerated motion, okay? When the acceleration is constant, and we can find a constant acceleration in real life very easy. That's what we're gonna discuss in a little bit, okay? So the theory for the one-dimensional constant acceleration motion is these 3 equations on slide 6. They're called kinematic equations, okay, in one dimension. So they can be proved. They can be proved using the definition of velocity, acceleration, but we're not going to prove them here. We're just going to use them, okay? So again, some of you may have already seen these equations before. The first equation helps you predict the velocity at any point, okay? You pick a final point, you use the initial point, initial velocity at an initial point. You can always predict the final velocity. And then the second equation helps you predict the location of this object after a certain amount of time. Okay, so this xf is the final position of this object. And then the third equation actually can be derived. So the third equation is not an independent equation. It can be derived using these two equations, but we're not going to derive them here. And this equation, in some cases, can be very useful. Okay, so that's why we also list that as another kinematic equation. So these equations are the theory you're going to use when you see a constant acceleration motion. Okay, so you always manipulate these three equations. Sometimes you use one of them, sometimes two of them, and sometimes you use you need to use all of them to find things you need. Okay. All right. So a constant acceleration motion, if you make a position and a time graph, okay, take a look at the plot at the top on this slide 6. You're not going to get a straight line, right? Because the slope, which is still the acceleration, which is still the velocity, is not a constant, right? In this process, so you're going to get like a curve. You're going to get a curve, and the slope is changing everywhere because the slope is the velocity, and velocity changes in this case. But if you make a velocity versus time graph, you will get a straight line because now the slope becomes the velocity over time, so that's going to be the acceleration. And if it's a constant acceleration motion, you should get a straight line. The slope is the same. So the velocity increases with time linearly. Okay, so they have a linear relation. Okay, so and these equations, they're going to be given on the test. As I said many times, you don't need to memorize a lot of equations in physics. That's not what we're doing in physics. Some people had this impression, okay, that physics is all about memorizing equations and plug numbers in equations, but no, physics is not. Physics is about understanding it's about discovering the theories, the laws in nature, okay, but we don't really need to discover them here. We're just learning them, right? But also apply these theories, the laws, in the real life example, okay, and then do the math. That's the most important part, okay. Set up the problem using the right law, the right theory, and then do the math and then get the right answer, okay. So for these fundamental equations, you don't need to memorize them. And these definitions, a lot of things that they are defining equations, you don't need to memorize them, right? Okay. Now let's practice this theory in a real problem. So let's take a look at a question on the next slide. When you start a car, it attains a speed of 15 meters per second in 4 seconds. We want to find the distance the car travels in this time. Okay. So let's draw it out. So something moving, right? It's a car moving, but it's an object. Okay. So this car is moving, and then it's also accelerating, okay? Because you're starting this car. So after 4 seconds, it's going to reach 15 meters per second. So this is 4 seconds. After 4 seconds, we want to find the distance the car travels. Okay, we want to find the distance the car travels. So let's assume this is a constant acceleration motion, okay? To simplify this question. Now, if I want to find the distance travels, okay, so I can set up my origin here, right? I can say the very beginning of this motion is the origin, okay? Because it's a coordinate system you set up to help you do the math, okay? You can always set up the coordinate system any way you like. You can always set up the origin, at any point you like. So we usually set up the very beginning of the motion as our origin. So we make like xi equals 0, right? So I say this is my origin. So the x starts here. Of course, the position of this car at this point is going to be xi equals 0. Okay, and this is a one-dimensional motion, so I don't need to worry about vertical motion. There's no motion in vertical direction. So the xf, if this is 0, and if I can find the position of this car at this point, that is the distance it travels, right? That is the distance from the origin, which is the initial point of this motion. Okay, so in this question, I need to find xf. Let's see. If I assume this is a constant acceleration motion, it's gotta be this theory. It's always this theory, okay? In this class, okay, kinematic equations, when you see constant acceleration motion. xf, okay, so you can, in principle, you can try either the second one or the third one. You see that both of them have xf in it, okay? So let's try the first one, the second one. If the second one doesn't work, we can try the third one, okay? Sometimes you don't pick the right one in the first place, okay? Because there are always 3 equations you can choose, okay? And if you realize it doesn't work, that's fine. Just try another one, okay? Now, let's see. If I want to use the second equation, right? So I would need this xi, which is 0, because I already set my origin at the initial point, at the very beginning of this motion. So that's nice. Now, initial velocity. Initial velocity, it's gonna be, what is the initial velocity of the car when you start it? When I start a car, of course, initially it's not moving. So initially, the velocity is 0, right? So I get another 0 for the second term, which is nice, right? We like zeros. That means we don't need to worry about them. So the only term I need to calculate is going to be the third term. Get the square here, okay? Now you see that the time is given, right? The time of this process is 4 seconds. So I do know this number. So the only number I don't know from the problem is the acceleration, right? Okay? So that just means you can solve this problem in one step using one equation. You need to use another equation, another theory to find things you need in this equation first, okay? So you're gonna do this, you're gonna solve this problem in multiple steps, okay? Not all of the problems in physics, one step, one equation, I plug numbers in, I get the answer. That's the simplest question, okay? And you don't always get the simplest, the easiest questions, okay? So that's my direction, okay? That's strategy. Okay, I need another equation to help me find the acceleration so that I can plug in to this equation and then get the distance the car travels. How do I find the acceleration? Again, take a look at these 3 equations, right? So I used the second one, so I could use the first or the third one to find acceleration for me and then plug it into the second equation, right? So which one do I use? Well, I can't predict. Let's just try one. If that doesn't work, let's try another one, okay? Let's try the first one. If I want to try the first one, I would do this, right? I would first rearrange this equation. Rearrange this equation, I would get an expression for AX, okay? And then if I know everything else in this equation, I can use this rearranged equation to find the acceleration, then plug it in, right? So let's see. First of all, you know how to rearrange equations, right? That's some basic algebra you should know. Now let's see if I have all the numbers I need. What is the final velocity? Okay, 15 meters per second, right? That's the velocity at this final point, if I call this the final point. Now the initial velocity of 0, we figured, right? Because someone starting the car. It starts definitely from rest. And the time is given, okay? So once I rearrange this equation, get expression for AX, I should be able to plug all the numbers in from the question and find the acceleration and then plug it to the second equation, okay? So that I can find the distance it travels, okay? So now you can pause the video and then find the answer, and then compare your answer with mine. Okay. All right, so let's see. So first of all, let's rearrange this equation. If you rearrange this equation, what do you get? You will get Vxf minus Vxi over delta t. And this is just changing velocity divided by changing time. That's just definition of acceleration. So actually this equation has been derived from the definition of acceleration, right? So that's what I said. These equations, they can be derived, okay? So we didn't derive them here. We're just going to go ahead and use them, okay? Now plug numbers in. 15 meters per second minus 0 divided by 4 seconds, okay? So what is the number? So the number I just got was 3.75. meters per second square. Okay, once I have that, plug the number into the second equation so I can find the distance to travel, the final position of this car. So if you do that, don't forget the square, don't forget the half. That's a common mistake people make, especially on the test when they are very nervous. 30 meters. Okay, so in 4 seconds, it's going to be 30 meters. All right, so that's how we use this theory to calculate the distance the car travels in 4 seconds. Okay, so some people, they may say, well, okay, I don't really care when I start a car how much distance it travels in 4 seconds. So why are we doing this? Well, remember, this is an intro-level physics class. We are practicing these theories, the laws, okay, in an intro-level class. Of course, the problem we see, they're going to be simplified, well-designed problems so that we can solve them in 5 to 10, 15 minutes, okay, in this class, okay. We're not going to really get a physics project, a real-life physics project that's usually going to take months or years to finish in an intro-level class, right? But the theories and the laws are going to be the same. So that's why we use this simplified. Sometimes they seem even a little bit silly to you. Why do I care this? Why do I care that? Because they're simplified. They're well-designed problems for an intro-level physics class when we don't have much time, we don't have months or years to spend, and then we just start learning the very fundamental, very basic laws and theories in physics. Okay? So a lot of problems you see in this class, they're going to be, they will be related to life, real life, but they will be very simplified, very well-designed problems. We can solve them. We can practice the theory and laws, okay, in a very short amount of time, okay. So that's the idea. That's the idea, okay. But the theories for real physics project in real life, okay, the theories and then the laws they use, okay, the physicists are going to be the same, okay, but the details are going to be very, very complicated. Think about that, right? If NASA wants to send a spacecraft to the Mars, okay, to explore Mars, okay, of course they want to know every detail of the motion of the spacecraft from the Earth to the Mars, okay? They even need to monitor this process, okay, all the time, okay? Then how do they make predictions? How do they finish this project? How do they make sure that the spacecraft will land on Mars, okay, when they launch it? Okay, they're going to do a lot of calculations before they launch it, right? And it may take them years to finish this project, okay? But when they calculate the position, the velocity of the spacecraft at a certain point, the theories they use, okay, it's going to be the same theories we use in this class to predict the velocity, the acceleration, the distance an object travels, okay? But of course, we cannot do that calculations in a class like this, right? Okay, we don't even have those fancy, computers to help us do that, okay? So we would have to use some simplified, well-designed, sometimes look really silly problems to practice laws and theories, okay, in an intro-level physics class, okay? So that's what we're doing in this class, all right? Now let's take a look at the next question. So the acceleration, even though we call this a variable acceleration, this a, okay, but we know that in real life when the velocity changes, right, something has a velocity, it's moving, the velocity changes. It can be accelerating, it can also be decelerating, okay? So how do we distinguish them in physics? Again, it's pretty much like how do we distinguish left and right, up and down? We don't use words, okay? We use signs. So let's take a look at the next question, okay? So we're going to see how we represent deceleration, okay, in physics, still using the same variable, this acceleration we define, this a. So take a look at this question. So I'm sure that this may have happened to a lot of people. It happened to me a couple of times. Say if you're driving down the highway late one night at like 45 miles per hour, and when you see a deer steps onto the road in front of you, okay? So of course you don't want to kill the deer. And then, if you collide with the deer, it's also dangerous to your car and yourself, right? Because the impact is going to be really, really huge. So of course, everyone's going to do this, right? Everyone's going to slap on these brakes to stop the car as soon as possible, as hard as I can, right? That's what I would do. So remember, there's always some reaction time in this process. Even though you can do that really fast, okay? There's still a reaction time in this process. Say you can stop your car, okay, in 0.2 seconds. That's already really quick, okay? We're going to assume, again, the acceleration is constant. I want you to find out how far the car will go, okay? So the car is not going to stop as soon as you stop, you hit the brakes, right? It's going to still move a certain distance after you slam on the brakes, okay? Because there's always a time for this car to stop. So I want you to find how far this car goes after you slam on the brakes, okay? So constant acceleration motion, as I just said, it's always the same theory. It's always the same theory, okay? That's why I like physics, okay? You always use the same theory, okay, for different things, okay? Okay? So it's pretty much like this, right? See, this, the car is moving, right? And then it's, we want to find the final position of this car at some point. I can still call the very beginning of this motion origin. So I would say xi is 0. If xi is 0, I want to find xf, which is the distance the car travels. So even the model is the same. We can still model it the same way as we just did, right? We just get different numbers. How do I find xf? I would still try the second equation because I just solved the problem. I have some experience now, okay? So why don't we just do what we just did, okay? See if I can solve the problem the same way. I tried the second equation. I already have xi because I set up my origin as the very beginning of the motion as my origin, 0. What is the initial velocity? Okay, now the initial velocity is not 0, so right? Because we just learned that this guy has an initial velocity. If I call the moment you see the deer and then hit the brakes, okay, that's the beginning of the motion, okay. So the initial velocity, it's not 0. You can't put a 0 here. And the time the problem tells you, okay, it's a very short amount of time, 0.2 seconds. Okay, now and then the third term is still here, acceleration, 1/2 acceleration delta t squared. Okay, Now let's see. So this term you can calculate that because we have the initial velocity, we have the time, right? But you should watch the units. This is 45 miles per hour. You can't use 45 directly. You have to convert it to meters per second, right? Everything must be in SI units if you do math and physics, okay? So that's one thing I need to do, right? You can convert this to meters per second. That's going to be the initial velocity plug in. You can't plug in miles per hour because it's not in SI units. And then the second term, the third term, the time is given, right? The acceleration, you still need to find the acceleration, but I just solved a similar problem, I gained some experience. I could try the first equation, okay? So I rearrange this equation, this is still how I rearrange it. Now, do I know the numbers in this question to solve for A? What is the final velocity of the car? Well, if you're going to stop the car, at the end, the final velocity, it's going to be 0, right? So final velocity, initial velocity in meters per second, and the time is given, okay? You will have all the numbers you need to plug into this rearranged equation to find the acceleration first, and then plug it into the second equation, okay? And then you can find the distance the car travels. Now you see that even the steps are the same, right? The theory is the same, the steps are the same. The story is totally different from the story we just saw, okay? That's the beauty of physics laws, right? That's the beauty of these theories. You can use the same theory for different stories as long as you can model them, okay, the same, okay, use the same model for these two different stories, okay? So in this case, you will plug all these numbers in, and you see that you will have 0. 0 is the final velocity, minus something divided by time. If you do 0 minus something, you get a negative number, and then you divide it by the time, you get a negative acceleration. You get negative acceleration, what does that mean? That means this object is decelerating, it's slowing down, okay, which makes sense, right? In this problem, you are stopping the car. Okay, you are stopping the car, so it is decelerating, it is slowing down to 0, okay? You should get a negative acceleration. So that's how we distinguish deceleration and acceleration in physics, right? We still use the same symbol, we still call it the same name, we call it acceleration, but we use different signs. When we have a positive sign, we mean that this thing is really accelerating. Okay, it is getting faster and faster. When we use a negative sign, we mean this thing is decelerating, it's slowing down, okay? So we don't need to write words, and when we plug numbers in, okay, we should get the right answer. Because if you remove the negative sign, you plug it in, you plug in this equation, you're actually assuming that it's accelerating, which contradicts this problem, right? So you shouldn't erase these negative signs. These negative signs, they're meaningful in physics. Okay, a lot of people, they're so afraid of negative signs in physics. Whenever they get a negative sign, they just, they just think, oh, did I do anything wrong? Okay, let me just erase this negative sign. No, you don't. If you have done the math correctly, the negative sign is telling you something, and in most cases, it's telling you the direction, okay? All right, so now you can pause the video and then do the algebra, but one thing you need to do first is convert this 45 miles per hour to meters per second, right, okay? So in order to do that, the conversion between miles per hour, we have seen that before, right? Of course, you also need the conversion between hours and seconds. All right, so now you can pause the video and then do the algebra, okay? So let's see. So first, you're going to convert the 45 miles per hour to meters per second. So what do you get? Okay, remember how do you convert the units? You're going to use two fractions, right? And then you're going to put these four numbers in the right places, right? Remember we did that. earlier. So let's redo it one more time. This is going to cancel miles per hour. So 45 miles per hour, that's just going to be 45 miles divided by hours, right? So this 1 mile is going to cancel this 1 mile here, right? And then you want to cancel hours, you put 1 hour at the top, 3,600 seconds at the bottom, okay? This cancels this, so you will get meters per second at the end, right? The number you're going to get is going to be 20.1. Okay? So that's the Vxi. Now you can use this Vxi and find these, the acceleration, right? So the acceleration is going to be 0 minus this Vxi, and then divided by the time. Okay, so you get 100.5 meters per second squared with the negative sign because you get a negative number at the top, okay? And then you can go ahead and then find the distance it travels. You're going to plug the acceleration, the initial velocity, the time, okay, into this equation. So what are you going to get? If you do the math correctly, so this is going to be a negative acceleration, negative it is, don't erase this negative sign, okay? You're going to get about 2 meters, okay? So that means even if you see this, as soon as you see this deer in front of a car and you hit this brakes as soon as you can do, okay, it's going to still travel 2 meters. Okay, so it's actually still a very large distance, 2 meters, okay? So that's why you should always slow down when you drive at night, okay? Because you don't get a very good vision, okay? Even if you can stop the car really quick, it's still going to travel some distance, okay? Because of the reaction time, okay? All right, so that's these 2 questions. We use them to practice this theory, kinematic equations. Okay. So as I said, that constant velocity motion is actually very hard to find in real life, right? If you look around you, right, you can't find things moving at a constant velocity. Okay, very hard. Okay, to maintain a constant velocity when something's moving. But constant acceleration motion, okay, there is a constant acceleration motion you can find in real life, and it's very easy to find that. That's called free fall, okay? So some of you may already know that. What is free fall? Well, you just drop anything, right? It falls only under gravity, nothing else on it. Okay, that's called a free fall. So physicists have discovered that when something is in free fall, okay, you just drop something, it's falling totally free under gravity, nothing else on it. And then you can measure the speed of this, you can measure the velocity of this object after each second, right? And if you can do that, then you can compare these velocities, right? And physicists have found that the rate of the change of the velocity is actually always a constant, right? So that means the change in velocity divided by change in time is a constant. The rate of change is a constant. So that means the acceleration in this motion is a constant. And this acceleration has been measured to be 9.8, okay? So this is a very, very famous physics constant, okay? I'm sure that everyone knows that, okay? Because that's the constant used to calculate gravity, the weight of anything, right? So this is called free fall acceleration. And then we all use this symbol, little g, to denote this acceleration, okay? Okay, so I call it little g or free fall acceleration. Some people just call it gravity. Okay, it's a little bit confusing because sometimes when we say gravity, we mean the force. Okay, so I don't like calling this guy gravity. Okay, I usually call it little g or free fall acceleration. Okay, when I say gravity, I usually mean the force. Okay, all right. So then anything in free fall, okay, if you drop anything in free fall, so their motion is going to be the same. They will always have the same acceleration, because that has been verified in experiments. Okay, so that means a very interesting conclusion would be this, right? If you drop two things at the same height, okay, you let them go at the same time, their motion is going to be the same, right? So the velocity of them is always going to be increasing 9.8 meters per second for every second. So the first second, if you look at the graph on slide 9, first second, they will all get to 9.8 meters per second. The second, the velocity is going to become, both of them, 19.6 meters per second. So their motion is going to be exactly the same, right? You can't distinguish their motions. You can only see they're two different objects, but their path, their velocity, the distance they travel, it's going to be exactly the same at every second. So of course they will always reach the ground, reach the floor at the same time, right? So you can do this experiment, right? It is said that Galileo, have done this experiment, right? This is a very good story. Galileo is said to have dropped the two balls of different masses from the Leaning Tower of Pisa to demonstrate that the fall time was independent of the mass, okay? But most likely this story is not true, okay? Good stories are usually not true stories, okay? But anyway, so and this experiment is very easy to do, right? You just grab two things, like if I drop this marker and this pen, they will definitely hit the table at the same time, okay? Because they're both in free fall. Their motion is exactly the same. You can use the exact same theory to predict the velocity, the distance it travels at every second, and it's going to be the same, okay, for them. You notice that in this theory, there's no mass here, so it's regardless of the mass. Okay, it doesn't depend on the mass, okay? So then if we do this, right, if I say I pick a very light thing, okay, I don't use the pen and the marker, I compare the marker and a piece of paper, then the piece of paper is not going to be reach the table at the same time with the marker, right? So what is going on here, okay? So that's because air resistance, okay? Air resistance, okay. There's air resistance on the paper, okay, which definitely slowed it down, okay. Is there air resistance on the marker? Yes, there is, okay. But compared to its own weight, its own gravity is negligible, okay. So for a piece of paper, because it's very light, the air resistance is comparable to the weight. So you can see the effect of this air resistance, okay? It's going to slow down this piece of paper significantly. For this guy or this guy, we're going to do the calculations later. If you calculate, even if you consider the air drag, okay? Because compared to its own gravity, it's very, very small, okay? So it's not going to really affect the motion of these guys, okay? So it's going to be really hard to tell the difference with and or without air resistance. So that's why, like normal things you pick, you do the experiment, they were always in free fall and they will always reach the floor at the same time, okay? So if we can get rid of air resistance, right? And then even if you drop a marker and a piece of paper or a hammer and a feather, they should reach the ground at the same time, because our resistance is gone. They should both in free fall. Their motion is exactly the same motion. There's no difference, okay? So of course you can do that on the Earth. Well, actually we can, okay? You have to use air pump. You put some these things in a tube, and then you use air pump to get all the air out of the tube, and then you drop two things like a coin or a feather. They will get to the bottom at the same time. But a cool thing, this astronaut David Scott, he did on the moon, okay? So that was during the Apollo 15 mission, okay? This astronaut David Scott, That was in 1971. I think that's before like you were born. Okay, that's even before I was born. Okay, so he did this very famous free fall experiment. Okay, he just dropped a hammer and a feather at the same time, and because on the moon there's no air, so there's no air resistance, and they reach the ground at the same time. Okay, so you have to believe that you can do experiments. Okay, all right. So I attached the link to a video, YouTube video. You can take a look at this YouTube video. Okay, it's amazing. It's a very beautiful theory. Okay, so he did this experiment on the moon, and these two things, a hammer and a feather, they reach the ground at the same time on the moon. Okay, all right. So okay, a few points I wanted to make about free fall. Okay. So first of all, as I just said, any two objects, we already know that if you drop them at the same height at the same time, if the air resistance can be neglected, like very, very small compared to their own weight, they will always hit the ground at the same time with the same speed, right? Regardless of their shape, their size, their mass, or what they are made of. Okay, so that's a conclusion from this theory. Okay. Now, when air resistance cannot be neglected, okay, like a piece of paper, it's going to definitely be slowed down significantly. So it's not free fall anymore. So you don't compare that with another thing in free fall, right? And you say that this doesn't make any sense to me because it's not in free fall anymore, right? Okay. So a very good example is the skydiving. If you see the parachute diving, okay, before and after the parachute opens, you can definitely see a big difference. Okay, so after the parachute opens, it's going to get a very, very large air resistance. You can see the parachutist is going to be definitely slowed down significantly. Okay, and then because everything in free fall, it's going to have the same acceleration, right? So, and that's going to be true for any object in free fall. They all have the same acceleration, little g, and then the direction is always down because you drop any two things, they're going to move down. They never move up, right? Okay? And even if you throw something up or down, okay, they will still have the same acceleration of little g after they leave our hands, right? Even if I do this, okay, I know it's gonna go up and turn around and then drop to the floor. But in this whole process, only gravity is on it, so it's still free fall in this whole process, even though it's not falling all the way, okay, it's still free fall. So the acceleration is still the same. It's always 9.8 down. So even if you throw something horizontal or with an angle like this, okay, so we know that it's going to move in a parabola. It's not going to move in a straight line. Okay, we're going to study that in detail. That's actually called projectile motion. Okay, in that case, the acceleration is still 9.8 down. Okay, because again, once they have left our hands, only gravity is on them. So the they are still in free fall in a general sense. Okay, even though it's not falling in a straight line, but they're still in free fall. Okay, the acceleration is still little g, 9.8. And of course, 9.8 is only the free fall acceleration on the Earth, right? So if you go to different planet, the free fall acceleration is going to be different, and then the little g is going to be different. Okay, so but it's going to be usually a constant on a specific planet. Okay, so that's about free fall. Okay, as I said, this is a real constant acceleration motion in real life because we have verified that in experiments, right? Okay, so and in the next lecture we're gonna use this theory because free fall is a constant acceleration motion. That means I can still use this theory to make predictions in free fall, right? Because this theory is for any constant acceleration motion. So we're going to use this theory to study free fall in a bit more detail. Okay, we're going to solve some real problems. Okay.